Hello, and welcome to this presentation on the ACH580's application features. These features we are going to discuss today are pre-programmed features that come standard within the drive.
Before we get into the presentation, I'd like to introduce myself. My name is Richard Pexa, and I am a regional application engineer with the HVAC group at ABB. I've been with ABB now for around 2 years. Other HVAC experience I bring to the table, though, is that I used to work for Greenhack Fan for 4 years. While I was there, I had a variety of different roles. Before coming to Greenhack, I received my education at Marquette University, where I received a degree in mechanical engineering. The ACH580 has some great application-focused features, and today I want to talk about them. These features do a variety of things, ranging from saving cost, increasing reliability, and adding security. So here's on the agenda. First, we're going to talk about advanced damper control. After that, we'll move into motor disconnect detection. Then we'll talk about broken belt detection. After that, checksum, then event word, and we'll wrap it up with the custom auto reset of a fault. Advanced damper control. I would like to introduce the 3 control schemes that are included with advanced damper control. First, we have discharge air damper with no pre-pressure. Second, we have discharge air damper with pre-pressure. And third, we have outside air damper plus discharge air damper with pre-pressure. Advanced damper control is different than your traditional drive damper control, as it allows for the integration of both discharge air dampers, outside air dampers, along with what I like to call a pre-puff feature. This pre-puff feature has the motor spinning before the dampers open. So now let's take a look first at discharge air damper with no pre-pressure. Discharge air damper with no pre-pressure. In this application, we have one fan with one damper, and that damper is typically installed at the outlet of that fan. We're going to utilize the end switches that are either built into the actuator or the mechanical device that is affixed to the blade or near the blades of the damper. What these end switches do, though, is they give us the positive blade position of whether that damper is in the fully open or fully closed state. So how does this work? The drive will receive a run command. Once we receive a run command, the drive is going to command the damper to open. Once we get positive position that the damper is open, the drive will then command the fan to run. When the drive is done running the fan and receives a stop command, the closing sequence for this is just the reverse. So discharge air damper with no pre-pressure and all of advanced damper control is really easy to program. And we have a total group dedicated to this new feature, and that is Group 84. In a few slides, I'm actually going to run through how to actually program advanced damper control. But next, though, I want to talk about how this feature works both in automatic and hand modes. This feature, being able to work in automatic and hand, is great because there are times where you might not be able to be running the fan in automatic. Say there needs to be some maintenance done in an area and the drive needs to go into hand mode. You're going to see in the next few slides when we talk about the 2 other control strategies in advanced damper control that being able to run in hand mode is a critical feature. And finally, the reduction in troubleshooting time that comes with advanced damper control. There's a lot of great features that we call a timeout feature built into advanced damper control. And how timeout works, I'm going to describe on our next slide, can really help with figuring out what's going on in the system. So let's take a look. Timeout, I like to think of it as a troubleshooting aid. This is a feature that monitors the damper position through the auxiliary switches to provide added insight to what is actually going on in the system. This added insight can highlight with ease any trouble with airflow in a system. With the drive actively monitoring the position of the dampers, both the open and closed, this feature will drastically reduce troubleshooting and/or downtime due to damper failure. Timeout is a fully configurable feature and is designed to be configured to match your actuator's characteristics. The default setting is 30 seconds for open and 20 seconds to close. The full range of the available timeouts is 0 to 90 seconds. If a timeout does occur where the damper fails to open or close within those defaulted times, the drive can do three things. First, it can throw a warning, which is the default feature. Second, it can fault the drive. Or three, it can do nothing. I'm going to show you next, though, how easy it is to program advanced damper control on the ACH580.
So let's set up advanced damper control. Starting at the main screen, I'm going to go into the main menu and scroll down to parameters. Once I'm in parameters, I'm going to go into the complete list, hit the up arrow again to get to the bottom of the list so I can get to group 84 faster. Group 84 is now advanced damper control. Opening advanced damper control, we can see that we start on 8401, which when we go into shows us all three new control scenarios. In this instance, I'm going to select DA damper with no pre-pressure. Now let's go select our inputs for the auxiliary switches. For the open input, I'm going to select DI2, and next I'll go select the closed input. In our closed input, I'm going to select DI3. Let's take a look at the timeout actions. We discussed that it defaults as warning, but here you can see that it can either be no action, warning, or fault. We can see the timeout close there for the closing action. We can adjust that to the cycle time of the actuator. And again, we can see we can select if the damper doesn't close, we can go into warning or fault. So now we need to change the relay outputs. So let's go up to group 10 where the relay outputs reside. Once we get into group 10, we're going to go down a ways and find RO1 source. So 1024, you'll see that it defaults to damper control, but in this case, we're going to need to change it to source number 63, discharge damper control. When we go back and do this later, we can actually see we can also configure this for outside air damper control, but that can be used on a different relay. So let's go back to our main screen, and we can run the demo. Let's take a bird's eye look at our demo here. I'm going to start up the drive by giving it a start command on DI1. When I did that, the relay cycled, and we can see that discharge air damper is opening. Once we have confirmed that our discharge air damper is open, the auxiliary switch gave a signal to DI2, and DI2 started the motor to let it ramp up to speed. And now our fan is delivering airflow to the space. Once our fan has delivered enough airflow, we're going to remove the start command on DI1, and once the fan has reached minimum speed, the relay will actually cycle and then remove power from the actuator, letting it spring closed.
Now that we've gone over the fundamentals of how to program advanced damper control with more or less discharge air damper with no pre-pressure, let's apply this to discharge air damper with pre-pressure. Discharge air damper with pre-pressure. So let's talk about the application. So discharge air damper with pre-pressure is useful when we have a fan that's installed in a common plenum. And in that common plenum, we have airflow present. If that fan is not isolated, or if the damper is open before the fan starts, what can happen is that the fan blades could actually start freewheeling in the opposite direction. If there's too much momentum that's going in the opposite direction, the fan could actually fault the drive upon a start. So how does discharge air damper work with pre-pressure work? So what happens is the drive will receive a start command. Once we receive that start command, the drive is going to bring the motor up to a minimum speed before opening the damper. Once we've achieved that minimum speed, we're going to have the drive command that discharge air damper to open. Once we get that discharge air damper opened, we're going to get positive feedback that the damper is open on that end switch back to the drive. Once the drive sees that, the drive will release to control and follow the commanded reference. For how the closing sequence of this works, it's just the reverse again. Our final control strategy in advanced damper control, outside air damper plus discharge air damper with pre-pressure. So with this control strategy, we have the ability to control two dampers at once with all of the benefits of what we just described in the previous scenarios. So how this works, we have an outside air damper, which we typically think of that's installed upstream of the fan, and then we still have our discharge air damper installed downstream of the fan. So how this sequence works is that when the drive receives a run command, the outside air damper will begin to open. And once we get then confirmation that that outside air damper is open, the motor will then start to run to the minimum frequency. Once we have hit our minimum frequency, the drive will then command the discharge air damper to open. Once the discharge air damper is confirmed open, again through those end switches, the drive will then ramp the motor up and then follow the commanded reference. The closure sequence of this, though, again, is just the reverse. If you would like more information on advanced damper control, ABB has created a campaign site for this topic. The link to the campaign is at the bottom of the screen, but as you can see, here's a screenshot from the site. If you'd like to enter your information, you can download a copy of the tech note dedicated to advanced damper control. Also, we have pre-recorded a webinar for advanced damper control that you can click on and watch right from the website. The next topic I'd like to talk about today is motor disconnect detection. Drives are not always installed right next to the piece of driven equipment. This can be for many different reasons. Maybe the first reason that if the drive was installed on the piece of equipment, it wouldn't be able to fit in to the space that that equipment's going to live. Or maybe that piece of equipment is going to be installed outside, and we want to protect the drive from the harsh weather elements. So, per the NEC, if a piece of equipment is not within eyesight of a drive, a motor disconnect is required. So traditionally though, when we install that motor disconnect, an auxiliary contact is brought back to the drive, so the drive can monitor the open or closed status of that disconnect. Well, when we install this motor disconnect, some extra things have to occur. Well, we have extra labor to install that disconnect, and then we also have extra costs and materials. And the major cost of materials is that we have to run additional conduit from the motor disconnect back to the drive. And the reason is that we are using a low voltage auxiliary contact. We are not able to put that low voltage wire in the same conduit that's leading to that motor disconnect that houses the high voltage motor wires. So some issues may occur though if we don't actually have that ability to monitor that position of that disconnect. If the disconnect is thrown in the off position and someone says to start up that drive, when someone goes to open or close that disconnect while the drive is running, an overcurrent event can occur. ABB has created an alternative solution to where now we do not need to wire back an auxiliary contact to the drive. In the ACH580, you might be wondering, how do we do this? Well, in the ACH580, we monitor all three output legs of current going out to the motor. So with the drive being able to monitor all three legs of current, we are able to know that when all three phases of current drop out, we can assume then that a motor disconnect has been thrown. So this is a really simple feature to activate. And how simple is it? Well, you go into parameter 95.26 and you'll see motor disconnect detection. You go into that parameter and you enable it and you hit save. On the next slide, I want to show you guys how simple this parameter is to program and actually show you it working in action.
So I have my demo set up in the lab and I'm starting it up, and I've started the drive in hand mode, but this feature also works in auto mode as well. I have the drive running and I'm going to open the disconnect. As you can see with the open disconnect, we get the output phase loss fault. So I'm going to reset the fault, and once the fault resets, I'm going to restart the drive and let it go back up to speed. You can see it's going back up. So now let's actually show off motor disconnect. So I want to program it in really quick. As you can see, I went to main menu and all the way down to parameters, and then I'm going to go into group 95. Once I get into group 95, I'm going to go down to parameter 9526. Once I'm in 9526, it's defaulted as disabled, but I'm going to enable it. Now that I have the parameter enabled, I'm going to start the drive again, let it get up to speed, and then I'm going to open the motor disconnect. You can see here that I just opened the motor disconnect, and a warning is now appearing saying motor disconnect switch open warning. As I go through, once I close that disconnect, the warning goes away and the drive ramps back up to the speed it was set for.
If you would like more information about motor disconnect detection, head over to our website, abb.com/drives. Once you're there, scroll down the page, and as you can see on the screen, my red arrow is pointing to Knowledge Base. Click on Knowledge Base, and it'll take you to a full list of all kinds of other supplemental information that we have. But specifically, look for TechNote 45, Motor Disconnect Detection.
Our next feature we're going to talk about is broken belt detection. Proof of flow in an application is really important to safeguard against maybe the loss of control of temperature in a conditioned space, or can even prevent equipment damage. And for example, that could be a frozen coil. So before VFDs became widely used, current monitoring relays or a current switch were required to detect if a motor lost its load during its application. So when using these current monitoring relays or current switches, extra cost was required to purchase that equipment, to run that wire back to the building automation system, and the commissioning time was increased because that current monitoring relay or current switch had to be tuned to match the application. Accuracy is also an issue when using that technology of current monitoring relays to monitor for if a broken belt occurs. And let me explain why the accuracy of using the current monitoring relays can be an issue on the next slide. Let me show you guys a couple graphs. So in this graph here, we're showing motor current. So the load in a typical HVAC application has a variable torque or a squared load profile. This means that load current increases with the square of the speed. Without any load, an induction motor draws only the magnetizing current, approximately about 30% of the motor's FLA. In the region below 66% of the speed, you can see in the graph that it shows very little difference between motor current between a lightly loaded and no load condition. This minimal difference makes an underload detection really unreliable in that region. I want to show you guys another graph. So in comparison, the second graph that I just put up shows how monitoring torque provides a greater difference between loaded and no load situations. Using torque as the basis for measurement makes detecting loss of load reliable down to at least 50% of the motor speed. This earlier and bigger difference between the blue and orange lines means that sensing torque and not current results in a more reliable and faster broken belt indication. The traditional current sensor solution for identifying broken belt conditions does not monitor torque. But, however, a drive calculates torque. Thus, a drive can be used to identify broken belt conditions instead of a current sensor. So let's take a look on the next slide how the ACH580 sets up the broken belt detection. Before setting up this feature in the drive, we need to collect a point of data. If it's possible, when commissioning the drive, run the motor disconnected from the load and record the percent torque value being displayed in the drive. Although what I just described may not be practical or possible in the application, the more typical technique is to run the motor at the lowest operational speed for that driven load. When we're at that speed and load, that will be our minimum torque required, so record that point of data. So how do we configure broken belt detection? First, we go into the main menu and go into primary settings. Once we're in primary settings, select advanced functions, and in there we will select under load detection to start the configuration. Once we enable under load detection, you will see that the source signal is already defaulted to torque. So let's go through the menu and configure the frequency point and load point to a value that's just below the data point we collected earlier. Now that we have this configured, let's next look at what you can do when the drive detects an underload condition. So in the event that an underload condition does occur, what do we want the drive to do? Under the action, when the underload detection parameter, you can see in the menu 3 options. First is a warning. Second, we can have the drive fault. And finally, we have warning/fault. Warning/fault works that if the drive reads a value under the underload point for half of the configured time, the drive will throw a warning. But if the torque value stays below the load point for the full time, the drive will then throw a fault. So along with then being able to throw a warning or a fault, using this feature, we can also toggle a relay. This relay can act as a hardwired connection to notify when a possible broken belt has occurred.
If you would like more information on broken belt detection, again, head over to our website, abb.com/drives. If you look again in Knowledge Base, you'll see we have a specific tech note 53, and this is dedicated to broken belt detection while using primary settings.
The next application feature I would like to discuss is Checksum. So let me introduce an application on how this feature can be very useful. A drive is used in an application where it is critical to know if any parameters have been changed. The drive could be in a mechanical room or any space that access to that space might not be fully restricted. Checksum is an added layer of security. The standard ways one could protect a drive would be to use the password function. The ACH580 does have a password protect option, but what can happen though is when an issue arises, the person on site does not know the password for the drive. The password might be kept with someone who is off-site and cannot give the password in a timely manner. Another option would be to run the drive without a keypad. But if an end user is worried about tampering with the drive, the one downside is that unless someone brings a keypad to the drive, if there's ever an issue, the use of hand mode is not available. So now that I've set the stage, let's talk about what it is and how it works. So Checksum is a feature that continuously monitors the settings of many of the parameters in the drives. So what the drive does, it generates a unique 8-digit hexadecimal number, and that hexadecimal number relates to how the drive parameters are configured. So if a parameter is changed in the drive, then the checksum value will change. So once we have set our checksum to the value that we want, we can also have notifications now occur if a parameter does change. So some of these notification options are, we can log an event, we can create a warning, we can create a warning and prevent a start, and finally, we can do a fault. So I've started this topic off with security, but on the next slide, let's discuss other ways checksum can also be a useful feature. I introduced checksum as a security feature, but as I pulled up this slide, you might be asking yourself now, why are there two checksums? Well, we know I just talked about the security of checksum, but now it's time to discuss how checksum can be a great tool when commissioning and troubleshooting. So let's define what checksum A is. Checksum A includes all user editable drive parameters, excluding the field bus communication settings. So when would we want to use this? Well, this would be a great tool when we're trying to compare drives that are the same size. So let's imagine an application such as a data center that has all of their supply fans configured the same way. An issue arises with one of their supply fan air handling units. In that unit, there are 6 supply fans that have a 15 horsepower motor, and then each motor is being supplied by their own drive, and were initially set up all the same. A quick way to troubleshoot would be to look at checksum A. If 5 of the 6 fans have the same checksum A value, one would be able to deduce that some sort of change happened to that drive. So checksum B, though, could be used very similarly. Let me define it. So checksum B includes all user editable drive parameters, but it excludes the field bus communication settings, as well as parameter groups related to motor data and energy saving settings. So when would we use this checksum B? It's when we would want to compare drives, maybe of like an entire site that were set up the same, but all have different but all the drives are different horsepower sizes. The next application feature I'd like to discuss is the event word. The event word is located at parameter 4.40 in the drive, and the event word is a word that contains 16 bits. You can think of this event word like being like another status word, but this event word contains a lot of information on what could be possibly going on in the drive. In these 16 bits, these all monitor a specific warning, fault, or pure event that occurs in the drive. Many of these bits do have a default value from the factory, but they all can be edited in the field to meet an application's needs. So all events that listed in the fault tracing section of the manual are available for use by entering their hexadecimal code in the corresponding bit. On the next slide, I really want to show how powerful the event word can be and how you can actually tie it to other parameters in the drive. So here, I want to show how we can use the event word and customize it with one of the relay outputs. So drive relay outputs are often monitored by control systems. The drive's default settings dedicate a single relay output for just a general fault status. But, when that fault occurs, you're not sure what fault actually did occur. So maybe there's a critical fault that you really want to monitor. So by configuring an RO source to correlate to a specific event can be a real powerful tool when a troubleshooting needs to occur. So I just kind of want to give maybe a possible application that this could work in. So let's say, for example, a facility may be experiencing power quality issues, such as high voltage transients that sometimes cause various equipment to fault or stop operating. The drive's flexibility, which allows a dedicated relay output to be programmed to indicate maybe, say, an overvoltage fault occurred, is huge. The knowledge that the drive faulted specifically on an overvoltage fault allows for a technician to more effectively troubleshoot the system then. And then they don't even need to be in front of the drive because they can see that, hey, this overvoltage occurred. So if the technician originally was only using, the generic fault status, they wouldn't possibly be able to know unless they were actually in front of the drive that an overfault occurred. And this can all be done by configuring, say, an event word bit to be then sourced for the RO, as I show it in the two screenshots to the side. The top screenshot is me configuring the overvoltage fault for that event word bit, and the second screenshot on the bottom is showing where going into group 10 in the ROs, you can actually have that RO source be event word 1 bit 4.
The final application feature I would like to discuss today is the custom auto reset of a fault. There are critical applications out there that may require a drive to always be running while a certain process is occurring. In the 580 family of drives, we have 10 faults that can be programmed to auto reset if they were to ever occur. In the auto reset selection, though, we do allow the end user one additional fault. The faults that are available for this are listed in the fault tracing section of the firmware manual. I would like to note, though, this selectable fault in auto reset can only apply to faults that do not require a power cycle. So off to the right, I'm showing two screenshots. The first screenshot on the top is highlighting bit 10, where you can actually turn on the selectable fault option. Once you get out of 31.12, which is the auto reset selection, if you go down to 31.13, this is where you can go in and put the hexadecimal code for the selectable fault that you would like to reset.
Let's summarize everything we discussed today. First, we went over advanced damper control. We went over the three scenarios that are programmed into the drive that meet most damper control schemes in the industry. We also saw that with advanced damper control, we're able to integrate everything into the drive, which then reduces additional integration into BMS systems. And we also saw that this works in both auto and hand modes. Next, we discussed the motor disconnect detection. We were able to see that the drive monitors the disconnect status without the need of an auxiliary contact being needed to be wired back to the drive, and that being a great time saver and also cost saver. Then we discussed broken belt detection. We discussed how motor torque percent is more accurate than current and is able to all be done through the drive without the need of additional piece of equipment. Then we talked about Checksum and how Checksum provided an additional layer of security. But also, besides being a security feature, we are able to see how it can be a troubleshooting time saver by being able to look at a lot of drives and checking how similar they are or how they may not be similar. Then we discussed the event word, how the event word could actually increase our visibility of what events are actually happening on the drive. And then we were able to see how we could configure an RO to monitor the event word that could actually trigger a relay output to actually signal an event actually occurred. And finally, we discussed the ability to customize the auto reset of a fault and how this is a great feature that could help reduce the possible downtime in critical applications.